A steam power system may need enormous turbines and pipes. Replace the steam with carbon dioxide and the rotor can become substantially smaller while still processing a large energy flow. More surprisingly, the carbon dioxide is not burned, consumed, or continuously released. It circulates inside a closed loop at a pressure high enough that there is no boiling boundary between liquid and vapor. Above about 31 degrees Celsius and 73.8 bar, carbon dioxide can enter its supercritical state. It remains a single phase, yet can reach high density while still flowing and expanding as a compressible working fluid. This combination enables a compact power cycle. But the turbine is only the visible part. To understand the potential advantage, we must follow the complete loop and discover why the flow divides into two branches before returning to the heat source. Begin with an indirectly heated cycle. Heat may come from concentrated solar energy, a reactor, industrial waste heat, or another high-temperature source. It does not mix with the carbon dioxide. Energy crosses a metal wall inside the primary heater. Because this is an indirect closed loop, the carbon dioxide inventory is charged and recirculated. The heat source supplies energy across a metal boundary, so the same core conversion process can work with different high-temperature sources without turning carbon dioxide into fuel or exhaust. Hot, high-pressure carbon dioxide enters the turbine, expands through rows of blades, spins a rotor, and drives a generator. The exhaust has surrendered part of its pressure and energy, but remains hot. Rejecting all of that heat and replacing it from the external source would waste much of the cycle's potential. The stream therefore passes through recuperators, which transfer energy to high-pressure carbon dioxide, already returning toward the heater. The low-pressure stream then approaches the cold side of the cycle. A cooler brings most of it close to the critical temperature, and the main compressor raises its pressure. The cold, high-pressure stream passes back through the recuperators, recovers retained exhaust heat, and returns to the primary heater for the remaining heat input. This simple-looking loop must operate under sustained high pressure. Shaft seals must limit leakage. Recuperators place streams with a large pressure difference on opposite sides of thin metal walls, while packing a huge heat transfer area into a small volume. Near the critical point, even a small temperature change can produce large changes in density and heat capacity. The enemy of every Brayton cycle is compression work. The turbine produces work, but the compressor takes some back to restore the working fluid to high pressure. If compressor demand becomes too large, net electrical output falls. Near its critical point, supercritical carbon dioxide becomes extremely dense. A given mass occupies less volume, so compression can require less work than for a dilute gas at the same mass flow rate. The most useful region is also difficult to control. Close to the critical point, temperature, pressure, density, and heat capacity do not change gently, as an ideal gas model would predict. A shift in compressor inlet temperature can change compressor work and mass flow substantially. Cooling under the wrong conditions may also move the system toward a two-phase region the compressor was not designed to handle. The recuperators create another problem. The cold, high-pressure stream and hot, low-pressure stream do not absorb and release heat at matching rates. Their thermal properties differ sharply near the critical region. A simple recuperator can reach a minimum temperature difference while useful heat still remains in the turbine exhaust. Transferring more would make the two temperature profiles touch or cross, so reusable energy must instead be rejected. How can engineers compress most of the carbon dioxide in its dense state without damaging recuperator balance? They use a branch that deliberately avoids cooling all of the flow. In a recompression cycle, turbine exhaust passes through a high-temperature recuperator, and then a low-temperature recuperator. The low-pressure flow divides. The larger branch passes through the cooler, approaches the critical temperature, and enters the main compressor. Because the carbon dioxide is dense, raising its pressure requires relatively little work. That stream then passes through the cold side of the low-temperature recuperator and absorbs heat from the exhaust. The remaining branch bypasses the cooler, It stays warmer and less dense, so the recompressor uses more work per unit of mass. Considered alone, that choice appears inefficient. But the warm branch does not need to absorb the same amount of energy in the low-temperature recuperator. After recompression, it joins the main branch after that branch has been heated. The split changes the heat capacity balance between both sides of the exchanger, lets their temperature profiles match more closely, and retains more exhaust heat. The combined high-pressure flow continues through the high-temperature recuperator and receives more energy before entering the primary heater. The external source no longer has to raise the working fluid from its coldest condition to turbine inlet temperature on every lap. It mainly replaces energy, converted into turbine work, and heat, that must be rejected to close the cycle. The advantage therefore comes from coordination. The main compressor exploits high density near the critical point. Recompression protects heat recovery. Two recuperators move energy from the back of the cycle toward the front. Low volumetric flow allows compact turbomachinery, compared with a steam system in a similar power class. Compactness also intensifies mechanical challenges. Large power passes through a small, high-speed rotor. Shaft seals face hot, high-pressure carbon dioxide. Recuperator channels need walls thin enough for heat transfer but strong enough for pressure differences of tens of megapascals. Materials must resist creep, fatigue, corrosion, and erosion through repeated thermal cycles. Better thermodynamics on paper do not automatically produce an inexpensive, durable plant. The full energy path now fits together. Heat crosses the primary heater into high-pressure carbon dioxide. The fluid expands through the turbine, converting part of its enthalpy into shaft torque and electricity. Exhaust heat moves through both recuperators. Most of the flow is then cooled so the main compressor can exploit high density, while the rest stays warm and passes through the recompressor. The pressurized branches reunite, recover more heat, and return to the primary heater. Each subsystem corrects a different loss. The cooler establishes the main compressor inlet condition. Recompression corrects the heat capacity mismatch. Recuperators reduce external heat demand. Compact turbomachinery uses low volumetric flow. Controls hold pressure, temperature, and split ratio inside the operating window, while materials and seals contain the process over a long service life. This is why there is no universal efficiency number. Performance depends on heat source and cooling temperatures, cycle layout, component efficiency, pressure losses, and recuperator effectiveness and cost. The United States Department of Energy is developing test loops and demonstration facilities to validate these interactions. Under suitable conditions, the technology may outperform many steam cycles, but durability, controllability, and economics still require demonstration at scale. A supercritical carbon dioxide turbine is not compact because carbon dioxide contains mysterious energy. High-pressure carbon dioxide carries a large mass flow through a small volume. The cycle can be efficient because most flow is compressed near the critical point, exhaust heat is recovered, and recompression prevents a thermal mismatch from limiting that recovery. The answer lies in the complete loop. High density reduces size and compression work. Recuperators keep heat inside. Recompression balances the thermal streams. Materials, seals, and controls make operation possible. That coordination, not the turbine alone, makes supercritical carbon dioxide a serious candidate for more compact heat-to-electric power systems.